Word video.
All right. So now tell me if it does it again. But you know, you can pay attention to the lecture. That's more important.
I don't understand where the trend coefficients are.
Well, there are 10 SIs and 10 sigmas. We're thinking of the case where they're 10 dimensionals. That's just 20. And these 100 are just made out by multiplying them in that way. Whereas over here, there could be 100 different coefficients, independent. Good question. Okay.
Could you please explain again? The coefficients, please. Could you please explain again?
Explain what again?
The coefficient.
Why there are 20?
Yeah.
All right, we're assuming for definiteness that S is a 10-dimensional space and sigma is a 10-dimensional space. So over here, in general, there would be 10 i's and 10 alphas. That would be 100 independent coefficients in general for an arbitrary vector in this direct product space. On the other hand, if you take a vector S in the space S and a vector sigma in the space capital sigma, then S is represented by 10 coefficients here. And this is specified by 10 coefficients sigma. And so the direct product, although it involves 100 terms, those terms are completely determined by these 10 coefficients and these 10 coefficients, which is to say by 20 coefficients. 20 being 10 plus 10. Okay, now if we use this similar notation for that direct product, then we can say that psi is a sum on I equals 1 to n, sum alpha equals 1 to k, I alpha psi, and then we would say that A cross lambda on psi would be sum ij equals 1 to n, sum alpha beta equals 1 to k, I alpha. So I'm going to write this in a double way. J beta psi, and this is also a sum ij is 1 to n, sum alpha beta equals 1 to k, I alpha, and this is really iaj times alpha lambda beta times j beta sum. Okay. Hope people can read that. All right, now finally your example. All right, this example is spin operator h bar over 2 sigma, where the sigma are the three power matrices, sigma 1 being 0, 1, 1, 0, sigma 2 being 0, minus I, 0, sigma 3 being 1, 0, 0, minus 1. So that's fine if you have one electron, say. But of course, as you know, there is more than one electron. There are more. And so you often have to do with 2 electrons or 3 electrons. So let's consider the case of 2. Then we have one operator, sigma 1, acts on one system, acts on the states plus or minus 1. And then we'll have S2 acts on these states plus or minus 2 for the second electron. Here I'm using the states, I'm saying that S3, 1 on plus or minus 1 is h bar over 2, is plus or minus h bar over 2, plus or minus of 1, and S3 operator 2 plus or minus sub 2 is plus or minus h bar over 2 plus or minus sub 2. Okay? So in this case then the operators A and lambda are the same except they act on different spaces. The one acts on the space of states for electron 1, the other acts on the space of states for a second electron. Okay. Are you okay? All right, we're all coming down then. What are the direct product states? The direct product states we can write as plus or minus, which is to say plus minus 1, plus minus 2, or if you want, plus minus 1, direct product plus minus 2. And of course, when I say plus minus, I don't mean it has to be plus plus or minus minus. It can be any sign for 1 and any sign for 2. So, for example, now these states that are direct product states are eigenstates of both of these operators. For instance, S3, 1 on plus minus is h bar over 2 plus minus. And S3, 2 on plus minus is minus h bar over 2 plus minus there. Okay. All right, this S2 acts on only this one, and S1 acts only on the first one. Now, what is the total, the Z component of the total, the third, what is S3 for the total system? Well, it's S31 plus S32. And these states are eigenstates of S3. In fact, S3 plus plus is going to be S31 plus 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 S32 plus plus. And so this is going to be h bar over 2 plus 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 h bar over 2 plus plus. And so altogether that's h bar plus plus. So this direct product state is an eigenvector of the joint operator S3 with eigenvalue h bar. In effect, it's a spin 1 system. Similarly, the state minus minus is an eigenvector of S3 because this is S3 1 on minus minus plus S3 2 on minus minus. And this guy acts on this one on that one, and so we get minus h bar over 2 minus 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 h bar over 2 minus minus. Altogether, minus h bar minus minus. Again, the sign of a spin of 1. On the other hand, the states plus minus are eigenstates of S3 with eigenvalue 0, because this will be S3 1 on plus minus plus S3 2 on the plus minus. And this will be h bar over 2 plus minus h bar over 2 plus minus, which is 0. Similarly, S3 on minus plus is 0. So these are eigenvectors of S3 with eigenvalue 0. Okay. Any questions so far? All right. Suppose we look at something more difficult now. S1 squared on plus. What is this? Well, this will be S1 1 plus S1 2 squared on plus. And the s's are, so this, we factor out the h bar over 2 squared, and we have sigma 1 1 plus sigma 1 2 squared on plus. But all of these Pauli matrices satisfy the rule sigma I squared equals 1. That is to say, I'm not summing over I. So sigma 1 squared equals sigma 2 squared equals sigma 3 squared. So this is h bar squared over 4 times 1 plus 1 plus 2 sigma 1 1 dot sigma 1 2 acting on plus. And so that is h bar squared over 2 times plus h bar squared over 2 sigma 1 1 on plus crossed into sigma 1 2 on plus. Well, sigma 1 looks like that, and just to see what this actually is, 0 1 1 0 on plus we represent as 1 0, and so this is equal to 0 1. So sigma 1 on sigma 1 k, say, on plus of k is equal to minus of k. So this is then minus and minus. So altogether this thing is h bar squared over 2 times plus minus. So that's what sigma 1 squared does to plus. Plus isn't an eigenvector of sigma 1 squared. Instead it gets mapped into h bar squared over 2 plus minus. All right, the rest of that exercise is problem 18. Okay, let me switch now to density matrices. Question? Yeah.
Oh, since this is rather new to me, this is rather new to me, so I was just wanting to clarify what the superscripts and subscripts were.
Well, the subscripts refer to the three directions of space: x, y, z, 1, 2, 3. The superscripts refer to which electron you're talking about. So the things in parentheses mean electron. Well, except for, of course, here, that's squared. It's, I'm just repeating what's in the notes, so it should be. The writing in the notes is better than the writing in the book. All right, let me skip to this blackboard. Yeah.
Before we go on, how did that turn into a minus again?
Well, sigma 1 is this matrix. And the plus state is, in other words, we're using a certain, in the plus minus basis, the vector plus is 1, 0, the vector minus is 0, 1. So plus is represented by 1, 0, minus is represented by 0, 1. And
Oh, I see.
sigma 1 is represented by this, so sigma 1 plus is minus.
The definition plus state equals to 1, 0 is the definition.
Yeah, it's, in other words, it's a choice of basis, effectively. Okay, and also a convention. In other words, well, here, let me go over here then. In general, if we had some arbitrary basis, you know, then that would be some complex number, and that would be some other complex number, and A minus would be another one, and A minus and B minus would be another complex number. But we choose as our basis the vectors plus minus themselves. And so the top component is plus plus, and the bottom component is that, and then this thing is then 1, 0, and then plus minus 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 then gives us 0, 1. So in general, these vectors plus the vector plus would be represented like this, and the vector minus would be represented like that. But to make life simple for ourselves, we choose as A equal to plus, B equal to minus, and then these turn into that. And then the matrix there, when we say sigma 1 is 0, 1, 1, 0, what we mean here is that the plus sigma 1 plus is 0. That's the top left matrix element. We say minus sigma 1 plus is equal to 1. That's this guy. We say plus sigma 1 minus is equal to 1. That's this guy. And we say minus sigma 1 minus is 0, and that's this one. So that's the sense in which this matrix represents sigma 1. It's in the plus minus basis. This is the matrix representing sigma 1. Is that, yeah?
This is unrelated to that. I will sort of related, but when you use the concept of the tensor product,
Yeah.
is that simply just writing the state, or writing the state as just like the plus comma minus 1? Is that when you use the tensor product between the two particles?
Like here.
Yeah, is that simply just using the? I mean, do you just use that concept when you just write plus, comma, minus, like what the state of one, comma, the state of the other?
Right. In fact, I'm a little bit puzzled as to what happened here. I erased something. So, in other words, this particular thing would be, yeah, that's what I erased something.
that's stupid. It's just the same thing, isn't it? In other words, we're going to be using plus minus comma plus minus is then defined as plus minus system 1 cross plus minus system 2.
I mean, is that the only spot we use the concept of the tensor product here, I guess is what I'm asking?
Well, it's used all the time in physics because we all the time have different spaces.
No, I mean just in this problem I'm asking. Where did we, other than just...
Yeah, in this problem for two spins, this these four states, plus plus, minus minus, and plus minus, and minus plus, those four states span the four-dimensional space that's of the two spins. Good question. Okay, are we done with that? All right, let me say something now about density matrices. If you have a pure state, which is to say that you've prepared this a set of identical systems, and or to put it differently, you know that whatever's coming in this beam, say, you know everything about the state. Like it might be a hydrogen atom in its ground state, the electron spin is up, the nuclear spin is up. Okay. As far as we know, that's all you can say about the hydrogen atom. Or you say it's a photon and it's got certain momentum, circularly polarized, positive circular polarization. Well, then you'd say it's in a pure state. The density matrix that describes that pure state would simply be the outer product of the ket and bra that represent that pure state. And then any physical operator, say Q, the mean value of Q in this state, you can write it as psi Q psi, but you could also write it as the trace of rho times Q, because that would just be the trace of psi psi Q. And now if you perform this trace, you want to perform the trace by performing a sum of diagonal matrix elements phi, psi, psi, q, phi, summed over a complete set of states phi. Well, the sensible way to do that would be to choose a set of states phi to perform the trace, such that one of the states was the state psi itself. Then if these states are orthonormal, this inner product would be 0 except when phi is equal to psi. In that case, the value would be simply psi q psi. So that's how density operators work for pure states. And then the value of any physical operator is just the mean value in that state of the operator Q. If, on the other hand, you have a system that's not a pure state, well, then you might know that the system is maybe in the state psi 1 or it's in the state psi 2, and you might say that it's 2/3 of the time here and 1/3 of the time there. Okay. So how do you write the density operator for this? Well, you write it as rho is 2/3 psi 1 psi 1 plus 1/3 psi 2 psi 2. So that's an example of a density matrix of density operator. What you see, you can now go to the eventual, let's just notice I'm able to get away with this, by the way, as 2/3, 1/3. I'm assuming here that psi 1 and psi 2 are perpendicular, so that when I say it's either in state psi 1 or psi 2, that they're different cases. That is to say, if you do an experiment, you find it in psi 1 state, and then you measure it again for psi 2, you get 0. In that case, you see that these probabilities, of course, add up to 1. And you can think of this, if you represented this linear operator rho or this density operator rho in the psi 1, psi 2, or the normal basis, rho would be represented by a matrix 2/3, 0, 0, 1/3. And so you see this is a Hermitian matrix, and it's a matrix that has unit trace. So we're starting to see that rho dagger equals rho, trace of rho equals 1. Also, the eigenvalues are positive, and in fact, that's generally true because we could take as our operator Q the outer product of some state, I don't know, omega, say. Then the mean value of Q in the state represented by the density operator rho, then would be the trace of Q in rho, and that would be omega rho omega, and you'd expect that this would be non-negative because it's the probability that the system is in state rho, state omega.
Yeah.
That means then the diagonal elements of a density operator are non-negative, so that means the density operator is non-negative. These are the three properties then that define density operators. Any linear operator that's Hermitian, non-negative, and has unit trace is a possible density operator. And in particular, it has to be square since it's Hermitian.
You mean the components are non-negative?
No. Excellent question, though. Absolutely excellent question. Because remember, an operator is non-negative if the diagonal matrix elements are non-negative in any state. That doesn't mean, though, that every element of the matrix is positive. And in fact, I can just show you something. If you spin that camera around, this matrix here has matrix elements that are all non-negative. See, all matrix elements are non-negative, but the eigenvalues of sigma 1 are plus or minus 1. They're the same as the eigenvalues of sigma 3. Okay. In any event, so the more general case, instead of like this, the more general density operator, since it's Hermitian, you can always diagonalize it, and you can say that rho then is the sum pk kk, where k forms an orthonormal basis for this state. Pk greater than 0, the sum of the pk is 1, and the pk's are all real. Okay, so that's another way of writing a density. Since it is a linear operator with Hermitian, you can always find n orthonormal eigenvectors and write it in this way. Okay, so that's enough about density operators. Next time, I'll say a few words about correlation functions, which provide an example of non-Hermitian inner products, and then start Fourier series. I'm going to defer the group theory until we finish differential equations, which is after complex variables, which is after infinite series, which is after Fourier transforms. Sorry to keep you a little bit extra. I didn't really mean to.
Somebody have a pencil?